Lesson 1.1 is going to be patterns and inductive reasoning. And what that means is the inductive reasoning is looking at patterns and making conjectures. And we'll talk about what a conjecture is in a little bit. So again, inductive reasoning is looking at patterns and making conjectures. So let's talk about patterns first. So the first thing that we're going to kind of practice is describing a pattern. So you can have these patterns in a couple different ways. They can be pictures, they can be numbers. With the numbers, they could be adding, they could be subtracting, multiplying, dividing. They could be a combination. They could be every other number is negative. There's lots of different options. So what you're going to have is a couple pictures or numbers, and you're going to try to describe the pattern. So the first example that I'm going to give you is going to be a little square right here, okay? And then we're going to have an image that looks like this. And then we're going to have one that looks like this, if I can draw it correctly. Okay, and then the pattern's going to continue. So we're going to describe it first. So describing it, you're just verbalizing this. So when you look at that picture, what is happening from the first picture to the second picture? And then from the second one to the third one? Okay, to me, it looks like a stairway. So I'm going to say each figure looks like a stairway. But they're not all the same stairway. So what's happening? When I look at it, I'm seeing a row at the bottom being added with one more box. So you can kind of verbalize that. So it looks like a stairway with a row being added to the bottom. Okay, so that's describing your pattern. Then you might be asked to predict the next figure. So predicting the next figure. Well, if we're adding a row to the bottom so that it still looks like a staircase, I'm going to go ahead and redraw the one that I already have, the last one that's up there. And then I'm going to add a row to the bottom so that it looks like a staircase. And there's my next image. Okay, so there's one with pictures. Now we can also have them with numbers, so let's look at a couple of those. Because there's a lot more options, I think, on those. So we're going to describe the pattern and predict it. I'm just going to write that over here. We're going to describe and predict. Okay, so the pattern that I'm going to give you is 1, 4, 16, 64, and it's going to keep going. So we need to look at these numbers. What do I notice about these numbers? Well, how would we go from 1 to 4? To me, I would multiply by 4. So does that work with the second one? If I take 4 times 4, yep, I get 16. If I take 16 times 4, do I get 64? Yes. So my description would be each number is 4 times the previous. Now I'm going to predict my next term. Well, to get to the next term, what am I going to do? I'm going to multiply 64 times 4. 64 times 4 would be 256. Now remember, through any of this, if you need a calculator and you do not have one, there is a button on the home page of our Canvas page that's a scientific calculator. It's Desmos. And you are welcome to use that with anything that you need a calculator for if you don't have one. Okay, so let's look at another one. So number 3. This one's a little bit different, and we're going to describe and we're going to predict. This one's going to go from -5 to -2 to 4 to 13, and then the pattern's going to continue. So we're going to describe and predict. So what is happening in this one? To go from -5 to -2, what happens? I'm adding 3. To go from -2 to 4, I'm not adding 3, I'm adding 6. To go from 4 to 13, what are we doing? We're adding 9. So what are we doing? We're starting with 3 and we're adding the multiples of 3 each time. So starting with 3, we add the multiples, so 3, 6, 9, 12, 15, and so on. To each number. Okay, so what would my next term be? Well, we have 3, 6, 9, so my next multiple of 3 would be 12. So 13 plus 12 would be what? 25. Okay, so there's examples of describing a pattern. Now what I want you to do is pause the video after you write down this next one, and I want you to try one on your own. So let's get that example down, and this is the one that you're going to try on your own. So we have 9, 4.5, 2.25, and it'll continue. And I want you to describe it and predict the next term, just like we have been doing. So go ahead and pause and complete that. All right, now we're going to move on. There's a couple more terms that you need to be familiar with to start out geometry, and the next one is a conjecture. So what is a conjecture? Now that we can use our pattern skills, we're going to look at a conjecture. So a conjecture is going to be an unproven statement based on observations. So it's like a rule that we're going to write. We're going to look at examples and come up with a rule as to what we think is happening. Okay, so let me move down here on my page. So let's practice this. We're going to complete the conjecture. Those are going to be the directions. So complete the conjecture. Okay, the conjecture is the sum of the first n odd positive integers is what? Okay, so odd, so like 1, 3, 5, 7. Positive would all be above 0. Okay, and integers, numbers. So the first thing that I would do as soon as you have a conjecture, we need to figure out what that conjecture looks like. So we're going to write down some examples. The first odd number that I think of is 1. Well, 1 equals 1. The sum would be adding. So now I'm going to take 1 plus the next odd number, which is 4. I'm going to do it again. 1 plus 3 plus my next odd number would be 5 equals 9. And one more. 1 plus 3 plus 5 plus my next odd number is 7 equals 16. So what do I notice about these numbers? The first thing that pops out in my mind is they're all perfect squares. 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. But I don't want a number to be in my last and in the end of the conjecture, because I want this to be a rule for all of the examples. So this n, this represents the number. So for this question mark, we're going to fill in this statement with the sum of the first n odd positive integers is n squared. And that's going to complete our conjecture. Okay, so now I want you to pause the video again, and you're going to try one on your own. So go ahead and write this statement down, and then try to see what you notice about the statement. So your example that you're trying on your own is the product, remember product is multiplication, of any two odd numbers is what? Okay, so go ahead and pause and do that. All right, now let's come back together. We have one more term. We're going to talk about a counterexample. So sometimes our conjectures look like they would work for every example, but they don't. Sometimes they don't work. So a counterexample is an example that shows the conjecture is false. So this one's a little bit harder because you really have to think outside the box. So the example that I'm going to give you is for all real numbers, x is going to represent the numbers. The expression x squared is greater than or equal to x. Well, that's normally true. If I take 2, if x equals 2, 2 squared is 4, and 4 is greater than or equal to my original x, which is 2. So that would come out correct. But let's think outside the box here. If we think about maybe fractions and decimals, does it still work? Let's try a decimal, or even a fraction. Let's do 0.5 or 1/2. So if I set x to 0.5, let's try it. Is 0.5 squared greater than or equal to 0.5? If I take a calculator and I do 0.5 squared, I'm going to be at 0.25. Is that greater than or equal to 0.5? No. So x being 0.5 would be my counterexample. Okay, so last one that I want you to try on your own. So write this down and then pause the video. So your example that you're going to do on your own is going to be all prime numbers are odd. Okay, odd, so 1, 3, 5. Prime means that only 1 and themselves go into it. So like 5, the only things that go into them are 1 and 5. So go ahead and pause the video and try that one on your own.